Good morning, everyone. Welcome again to the third day of the EXA2PRO-EoCoE joint workshop. So today is our last day, and we'll start by the StarPU task-based programming hands-on session. So the session will last until noon and a half, and it will be composed of different presentations. The first one will be an introduction to the task-based programming model with StarPU. Then we have a first practice session targeting basic principles. Then we'll have a short break of 30 minutes. After the break, we'll have a more advanced a presentation about more advanced principles of StarPU, followed by another practical session. And in the afternoon, we'll have the linear solver presentations. So Samuel, I let you start.
Can you let me share my screen? Oh, I can.
Normally, you have the right to share your screen.
Okay. All right. So good morning. So I will introduce the StarPU and task-based programming runtime. The idea is that I will show the API. Really, we have seen the principles of StarPU the other day, and now we can look at the exact API, C API. So the first part will be on the basic principles, and we will see more advanced optimizations in the second part. So let's take an example. We have a vector that we have allocated on the stack, for instance, and we have a factor, and we want to scale the vector by the provided factor. So initially, you only have some source code which fills the vector with some values, for instance. So we have this. Now, what you want to do is to first provide this data to StarPU and then run a task that will do the scaling. So what you will need is virtual data, as I mentioned the other day. So what we call a vector, a data handle. So we call this a vector handle. And we call a function that registers the piece of data, so the vector here, and we get as a result the vector handle. So this is a value that is returned to the program after providing the vector, the number of elements, and the size of each element. So from this on, the application is not supposed to use this data anymore, because StarPU is in charge of where the data is. Is it on a GPU? Is it somewhere else on the disk or whatever? So it's not, the program itself is not allowed to access the vector array and only manipulate the vector handle through StarPU to modify the data. So for instance, one can insert a task which is doing some scaling of the vector, telling that yes, we will read and write the vector. So we modify the vector and provide a small factor for the task to execute it. And then we can wait for the task, because this call is asynchronous. So at this point, we are not waiting for the task yet. It's just going on asynchronously. And then we can wait for it and eventually unregister the vector handle. And from then on, the value which is in the array here can be looked at, displayed, etc., because it is not the responsibility of the runtime anymore where the data is. Okay, so that was a quick overview of what submitting a task after registering the data is. Let's see the details. So first, some terminology. So codelet, task, and data handle are the three main words that we will use in this morning. So first, the codelet. So that's basically a new word mostly. So for us, a codelet is just a notion of what kind of function you will do, which kind of computation you will do. So you have several implementations, for instance, of the vector scaling, a CPU1, a GPU1, an FPGA1, or even several implementations with different kinds of compromises. And you gather them into what we call a codelet, which simply lists the implementation. And then the codelet can be used to instantiate tasks. So basically, the codelet provides the information, the common information of the different tasks. So which kind of data does it take? Which are the pointers to the implementations of the task? So the codelet here gathers the implementations, and from there we can create different tasks. So we have two tasks here which perform the same kernel, because the kernel is described by the codelet. Okay, so now a task, that's a more common word. For us, it is an instantiation of a codelet. So it does compute something, some function. And what's interesting in the task is that it takes some input and produces some output, and it executes automatically, so from beginning to end, without getting interrupted. So we have the codelet that we have seen before, and then we plug, we know that the codelet can take some data as read and write, for instance, for the scalar, for the vector scaling. And then we instantiate a task which takes the data as an input and then computes the result and then emits the data output. So the data itself is a piece of data managed by StarPUs. So it can be of different types. That can be a vector, that can be a matrix, that can be a lot of different types. And this is what we give as input and output for a task. I mean, input and output that is managed by StarPU, in that it is kept in memory, it is managed really by StarPU. So the API is basically around these three notions. So declaring a codelet that can be quite often static in the program because your implementations are known statically at compile time. Then declaring the data at runtime, saying these are the data size and the storage area for the data. Then you have your function, the kernel function, and you can mix all together to get to submit a task and then wait for it. So let's look at the details, the programming details. So the codelet, which gathers the implementations, is simply a structure. So you have, for instance, a CPU implementation for the codelet. So you just provide it in a CPU func field. Then you tell about the data. You say that you have one piece of data, and you say that it is used as both an input and output. So it is in place modifications actually, since it takes it both at as read and write mode. So the task will get just one parameter, and it is allowed to read it and to write to it. But then you may have different sorry. And so let's look at the data itself. So you have your vector and you have the source code to fill the vector. And then you want to register it. So you have the register call which you've seen. And so from now on, you're only supposed to use vector handle. So you can do whatever you want. Submitting tasks, you can acquire, and we will see that later. You can submit a lot of tasks on the vector, and then eventually you can unregister the data. So the vector handle is destroyed. So you can, if you want to reuse the vector, you have to register again. So usually you do this at the very end of the application, just before maybe freeing the vector. Now the kernel themselves. So the function that was referenced from the Kotlin, since it's C, it has to have the same prototype for all kinds of computation. That's a bit of a pity that you don't have polymorphism in C, but okay, StarPU is a C library which allows for a lot of flexibility of integration in different kinds of languages. So we have to go through this. So we have two parameters, buffers, which will be the data of the task, and CLRs, which is the small data, some data that is not managed by StarPU. We will see later. So first, we get the first data of the task, and so we access the first element of this array. So it's a void star array because we don't know yet which kind of data this is. And so we cast this into a vector interface and to say this is actually a vector. I know this because that's how I wrote my program. And then I can look at it. So we have some macros here which check for the type of data and check that it is indeed a vector, and then get the attributes of the vector. So the number of elements and a pointer to the vector. So this macro is important, getting the pointer through the provided parameter, because StarPU might have made a copy of the vector, for instance, on a NUMA system. It may not give the pointer to the original location of the data, but to a copy of the data to make a local copy that can be accessed really efficiently. So the function here, the kernel function, is really not supposed to access some global variables like pointers and everything. It has all the information it needs from the parameters here, so the data, getting the number of elements and the pointer, and also the small factor. So we had a vector scaling example, so we need to know which factor we will use, and that can go through CLRG. So CLRG, we will see that's in the task and that you provide a pointer to the float parameter. And so here you can get it directly without having to register the data, etc. You just get a pointer as you have passed it to the task. And eventually you can do the actual vector scaling. So since you now have the pointer to the data, the number of elements, and then you can simply multiply the vector by the factor that you had set. Okay, so this is basically the kernel function. Then now, how do you submit a task? So we have a function which is called StarPU task insert, which does the submission quite easily. So it does insert a task in the DAG, so the task graph of StarPU, while generating the dependencies as I've described on Monday. So the idea is that you pass several arguments to the function. So first you pass it the address of the codelet structure. So that's here that to tell this task will perform this kind of computation. So here the vector scaling and computation. So now the task knows the different kinds of implementations which are available for this task. Then we provide the vector handle to tell you will work on this vector, and this is some data which is managed by StarPU. It is a data handle. So StarPU knows that it will have to transfer the data maybe on a GPU or something like this. And then it detects from the access mode of the data that this task will have to wait for any previous task which was producing the data, because we want to wait for the result of the previous task that rose to this handle before executing this task. And conversely, since it is writing to the data, then this task will be depending on by further tasks which will want to read this piece of data. And then eventually we have the factor of the vector scaling. So here we provide the address of a small variables and then its size, and say it is a value. So you can pass it not as a registered data, but just some small value that will be copied to the task execution. It's not efficient to always copy, but since it's a small factor, then that's fine. It's less expensive to just pass it like this in line than registering a data and registering, etc. So for small parameters, that's completely fine to do it like this. And eventually, you mark the end of the argument, because you can go on with several handles, several values as much as you want, and then you can just get the end of the argument. So you have to pass 0 to tell StarPU this is the end of arguments. A bit like the exec system call or something like this. You have to put a marker so that C knows that the arguments are over. Okay, so the submission is non-blocking, so it goes quite fast. It's like a few microseconds only to create the task and then submit to the scheduler. And then you can call it again and again and again to submit a lot of tasks, like we have seen in the Sholicity case. All of the submissions of tasks will be non-blocking. The dependencies will be computed at the same time. So just looking at the different access modes of the parameters of the tasks. And so StarPU will create a task graph actually while you are submitting the task. So you can do this really dynamically. That is, the tasks are starting to execute as soon as you start submitting them. And then while you are submitting tasks from the main thread, tasks start executing. So you will have a concurrency between the submission and the execution. So the order of the submission follows the submission order of the program with the addition of dependencies. So that's what we call the sequential task flow paradigm. And that is the submission source code looks like a sequential program. You just submit the task one after the other in the order that you would have in a sequential program. But then StarPU determines the parallelism from the data dependencies and executes in parallel whatever can be executed on parallel. So you can submit several tasks like this. This is non-blocking. And eventually you can wait for all the tasks to finish. So possibly like you have submitted all of the tasks of your program, and then you just wait for the computation to complete. So waits for all tasks that had been previously submitted. So getting back to our example, we have all the elements that we have seen before that are presented initially in the first slide, but here we have the whole example. That is basically what you will look at during the first hands-on session to make sure that you understand each piece, how they connect to each other. Yeah, and have a look at the documentation to check the details maybe. So for instance, the details of the parameters here. Okay, so now we not only have CPUs, but also GPUs. So the idea is to extend the codlet to handle heterogeneity. That is, we want to look at how we can express that we have different implementations on the CPUs and GPUs, and how can you provide the implementation for the GPUs. So first, you can provide several implementations, CPU implementations. So here we had an array, and so the array can be filled with several pointers to several functions. And StarPU will automatically determine which one is fastest for the data size and for the execution system based on previous executions. So when you first run your application, it will measure how fast the different implementations are, and then select at runtime which one is fastest. So here, for instance, we have SSE AVX. And you can also provide the information whether AVX can be used, for instance, depending on the capacities of the CPUs. Now, for GPUs, you can provide the implementations in some additional fields. So you have OpenCL and CUDA. So you just provide function pointers for these. And then let's look at how they look like. So for CUDA, we still have the same type of function as before, as CPU functions with the buffers and the CLRs. But this is really a CUDA source code. So we have to tell that this is an external C function so that it can be called from StarPU as it as it is used to. And then we have the same macros here and to get from the buffer the number of elements and the pointer. But here, this is a GPU pointer. So at this point, we are getting called as the implementation. At this point, StarPU will have already transferred the data on the GPU. So this is a GPU pointer, and this is not something you can inference from the CPU itself. You will have to pass it to the kernel function of the GPU. And you get the small factor. And this one, however, is a CPU function. It's not managed by StarPU, it's just passed on to the task implementation as it is. So this is CUDA, so you have to compute how many threads per block you want. So for instance, 64 threads per block. And then you look at the number of elements to process, and then you can distribute them to the different blocks. So you have different kinds of different number of blocks depending on the threads per block and the number of elements. And then you can actually call the CUDA implementation on the GPU, passing it on the number of blocks and the number of threads per block. So this is the common parameter passing to specify the kind of parallelization on the GPU. And also you pass something which is really important, is giving the CUDA stream to use to submit the kernel. This is really important because otherwise the default stream, the default CUDA stream brings a lot of synchronization, spurious synchronization with transfers, with data management and everything. So you really want to add this parameter, which doesn't change really anything in the submission, just an additional parameter so that things can go nicely. And then you have the actual implementation, which is simple on CUDA code that just takes the parameters that we have provided. So we have provided the vector and the scaling factor. So you have these, so the pointer inside the GPU memory and the factor, and then you can simply loop over it to multiply actually the vector. So that's it for CUDA. Now OpenCL is the same. I won't go into the details, but you see the structure is roughly the same. So get the pointer, ask StarPU for which kernel queue, and OpenCL program, load the OpenCL program to put it on some queue, then provide the parameters, and then tell us OpenCL, this is the kernel I want to execute, and then we have the kernel. So we have examples in StarPU to show this in details. I wanted to just show the Fortran case for people who need to use Fortran. The principle is really the same. We just have to adapt to the Fortran expressions. So the codelet is an allocatable pointer for Fortran. So we have a function that provides the allocation for this. So once you have your codelet, you can fill the different fields. So the CPU function for it, and the data access modes, so saying that I have a buffer which is accessed in a read-write mode. The implementation itself can be done in Fortran. So like in C, we have the two parameters, and the type of the parameters is always the same, like this. And then you have some functions to get the number of elements and the pointer to the actual data. And so here, this returns the val pointer. So this is a pointer, and you say it is some real. And you also specify Fortran that it has n elements. So you had to get the number of elements before this. And about the factors, you can get its content with some unpack arg function call. And then you can do the scaling as usual. So this is for the kernel. And then how do you actually submit a task? So you have your array. So you would use allocatable arrays with the varying size, and then you register to StarPU as for C. So you provide the location of the array, the number of elements, and the size of each element, and you get back a vector handle. So it is a CPTR, so opaque type. But then you can insert the task. You provide the codelet that you had allocated, the access mode, the values of the factor, and the size of the value, and then as usual you terminate the list of factors. So that was basically for Fortran. It's the same principles. So everything we will see in the tutorial are basically the same in Fortran. The bindings are really similar. So now we have the data interface. I mentioned that we have several kinds of data. So the vector, we've seen that you register telling the pointer, number of elements, and size of elements. But then you have matrix styles. So it is part of a whole matrix. So we have a big matrix, for instance, or just one small matrix. And what you specify is the pointer and the size, the number of elements in the tile and the size of it, but also here the number of leading elements. So when the tile is part of a big matrix, you may have several elements between each line of the tile. So you have to specify whether it is contiguous in memory or it is indeed part. It is a tile that is part of a bigger matrix. So you have to tell how many elements there is between each line of the tile. And we have a lot of different types of data. So for instance, BCSR matrices. So you have to pass on the indices, the raw PTR, the first entry. Depending on the type, you will have to provide different pointers, different size. We have the documentation for all of this. So we have also OOC, sparse matrixing, and etc. And this is extensible. You can provide your own type if you have, I don't know, complex numbers, a tree of data, or different kinds of types. You can actually describe the data to StarPU. The thing is, all you need to express to StarPU is the amount of data that is represented, and maybe several buffers of data, several pieces of data. So for instance, for BCSR, we have several arrays to express, but one matrix, one BCSR matrix tile is one data and several arrays at the same time. But for a task, you just pass on one data. So the way you express is really telling my piece of data is like this, and then to transfer on the GPU, this is how it is done. So we have 3 arrays, for instance, to transfer with this size, and StarPU will handle the rest. The last thing I wanted to discuss this morning is partitioning. So the idea is you have a big matrix and you want to parallelize the computation over the matrix. So when you want to split it in small pieces, so you can adapt the granularity of the tasks depending on the number of pieces that you will get. So what we have is notion of filter, which filters a piece of data. So here we have still our vector, which has been registered. So like we've seen before, and we want to split the vector in several pieces. So we have the function, the filtering function here, that knows how to split a vector, and we tell which number of parts we want. So the number of children data that we will get, and we call data partition that we provide with the handle and the filter. And from now on, the data is partitioned. So you're not supposed to access to the handle here anymore, and only access the data through the sub handles, so the small pieces of the data. So for instance, here, I'm getting the number of children of the handle and then can access the sub data of the handle. So the sub data number I in my I loop, and then submit a task on the sub handle. So here I have split my vector and run the computation in parallel on each sub handle. So all of the computation then can proceed in parallel since the sub handles here are completely independent. It's a partition of the vector. And eventually, once you have waited for all tasks to complete, you can unpartition the handle, and StarPU will collect all the pieces, all the small vectors that maybe have been computed on the GPU or whatever. So it will collect it all back into the original handle. And from then on, you can access the handle as usual. Okay, so that was it for now for submitting a task and partitioning. So we can move on to the hands-on session. I have sent, I believe, the link to the detailed content. So that there was the guide that we have sent previously, but I'm putting in the chat the address of the more detailed tutorial. So it has basically the same instructions at the beginning to explain the first example. Let me show it to you, what it looks like. So this is indeed the website I have passed the a link to. So it explains the basic example. So this is the simple version of the source code, but in the content of the archive that we provide, you will see that it's more detailed. We have more implementations. We have an OpenCL implementation and things like this. But this is basically the ground version of the vector scaling. And we go into detail into the actual calls to the functions and how we pass on the data and everything, and then how to run it, to check that it works, and then play a bit, like disabling the CPUs, disabling CUDA, so that you only let OpenCL be used, and look at how the implementation goes. And then an exercise is partitioning an example of matrix multiplication with some filters. And we also provide an example, a matrix multiplication example that is more efficient because it is using cuBLAS and CUDA. And then oh no, sorry, the partitioning here, it's not an exercise, it's an example. So an example on matrix multiplication. And then the actual exercise is to split the vector scaling into pieces, like we've seen in the slides, but then we do it again for real and check that it does actually work, that you do get some parallelism that is distributed over the workers. Okay, so one last thing is to execute this, we use the getting started guide section 2. We have explanations for running a Docker container so that you get all the dependencies. And in particular, you get the simulation dependencies. So this is explained in the, here when you build. So you have a make file, so you just have to run make to build at this point. But you will be able to look at the make file, how you are supposed to use StarPU, so the compilation flags and things like this. And the important thing is to be able to run the CUDA and OpenCL versions, even if you don't have a CUDA or OpenCL GPU, then you can use simulation. So this call here allows you to enable the simulation version of StarPU. Then you can recompile your example. And then when you run it, it will actually run in simulation, so that when you disable CPUs, you will see that it pushes in the task to the GPU. Virtually, of course, the computation don't actually happen because this is simulation, but all of the StarPU runtime will just act like on a real system with a GPU and CPU, all the scheduling and everything. So you will be able to really look at what you get, what kind of statistics of which task went to the CPUs, to the GPUs, etc. Okay, so I see a question in the pad. How is the virtual memory done? How do you manage to transfer the data to the GPU if you need it there? That is completely automatic. So the application doesn't have to tell anything about it. Once it has registered the data and inserted the task, then StarPU knows that it has to transfer the initial value of the data to the GPU and leave the value on the GPU if there is no pressing need for putting it back to the main memory, so that if another task wants to reuse the value constructed by the first task, then it will be able to just execute on the GPU immediately without having to wait for a transfer, because we already have a copy on the GPU. So the application writer really only has to care about registering the data, and then everything happens automatically. If the application wants to use its own type of data, it has to tell how to transfer. That is, this is, for instance, a BCSR matrix. So to transfer such kind of matrix, you have to perform 3 transfers for the 3 pieces of it. But that's all it has to tell. It only has to say, I have 3 pieces of data to transfer. And that's it. StarPU will know how to transfer with CUDA, with OpenCL, with other kinds of accelerators. So we have removed as much as possible the implementation pieces from what the application has to write. The API of StarPU is a bit dense, since it's a C API. So this is really not the same level of abstraction as SkiPU. But from the technical point of view, it abstracts all the details of what it is to offload something to a GPU, except the computation itself, of course. So the actual computation, you have to write it or to generate it from a compiler. Okay. Are there any other questions?
I have a question, not about necessarily the enzymes, but is it possible to modify or allocate the memory inside a StarPU task?
You can if you want, but that's a bad idea, because allocation, notably on GPUs, is awfully expensive. I mean, CUDA-free is a barrier. Okay. So it will synchronize with a lot of things, etc. So you can, if you really want, and for instance, as a first porting effort, you can just call your existing function, which does whatever you want with the GPU, as long as it uses just one GPU. So it can allocate free, etc. But it will not be efficient because it will synchronize with data transfers which are ongoing, possibly other kernels, etc. What we recommend itself is instead is to use what we call scratch. So what happens is you register a data, but giving it a null pointer, saying we don't provide a value for the data, but you register a data like a matrix tile, and you pass it on to the task, but with a scratch access mode, which tells StarPU this is temporary data. So don't actually transfer anything, just allocate something for me with the size I've asked for, and then I can get the pointer just like other kinds of data. And the good thing is that StarPU then will reuse the same buffer between tasks which use the same size of scratch. So it will allocate it once at the beginning of the application, and as long as there is no memory pressure, it will just reuse the same buffer all the time.
Okay. I imagine that if I'm not using GPU, it's less an issue. If I stay on CPU.
I didn't catch it.
If I don't use GPU, if I stay on CPU, if my code is only working on CPU, I think it's less an issue. I can.
Yes. Okay. Malloc is much less expensive, but if you have NUMA nodes, for instance, you would like allocation to be on the NUMA node.
Yes.
Malloc should be fine here. Local array on the stack will be fine as well. You can provide an initialization function so that the initial value of the scratch will be defined. And then as long as the task put the scratch back into the initial state, then it will be reused over and over by the different tasks. So you see, that's the kind of help that can be provided by the scratch.
Okay.
So I see that Orion is telling that CUDA3 is not a barrier in CUDA 11 anymore. At last. At last. It has been a pain for a long time, and we see people telling this is awful, I have a big barrier in my program. And yes, at last CUDA3 is not a barrier anymore. But yeah, it has been a pain for a long time. And possibly they have improved also the cost of malloc and free. That's why we really make StarPU do the allocation to factorize. When you have an application which basically manipulates only tiles, then it's completely useless to reallocate over and over. And StarPU has an allocation cache that allows to just have all allocated and just reuse the pointers without allocating all the time.
One question, maybe not very related to this, but the size of the task. So what if, for example, we do use codelets as part of, let's say, larger codes coupling, so that you use StarPU to create some kind of workflow between two codes or more as such. Is this something that was considered before, or is this useful? For example, I do need to try different interpolators, functions that actually comes with a huge library behind, and it seems quite fine to check and to provide or to design the interface as such that I can in future easily switch to another or improve or create a GPU version of it.
So for me, there are two things in what you're saying. So about code coupling, if your different pieces of code that submit tasks are all StarPU code, then that's trivial, because as long as they agree on the data handles that are used to transmit values between the tasks, then you can have several pieces of code that submit tasks, and it will be just one big task graph. And and then the scheduler will see it all. We also have scheduling context, which allows to partition the machine, saying I have a piece of the of my application which should go to this part of the machine, and this other part of my application that has to go to that other part of the machine. So when it's all StarPU that's like this, you just make the synchronization through data handles, like natural data dependencies. If part of your code is not StarPU, you can use data acquisition. I don't remember if I have this here. No, but it is explained in the manual. I'll put it you in the chat. StarPU data acquire. So StarPU data acquire allows you to say, now I want to wait for the tasks that have been producing this data. So for instance, in read mode, and from then on, you can access the data through the original array that you had initially. And then you can run some computations with it. So using the value you have obtained from the task. And then when you are done, you can call StarPU data release to tell StarPU, I'm finished with reading this value. You can execute, for instance, tasks that will overwrite it. Conversely, if you want to produce some data that will be used by other tasks, you can specify acquire in write mode to say, I will produce this piece of data, overwriting what was there before. So this will wait for any tasks that was reading the previous value of the handle. And then when you release, that unleashes all the tasks that has been submitted after the acquisition. So still in the sequential order. So that's a way you can plug several pieces of application coupling, be they StarPU-fied or not. Then there's another thing, which is porting to GPUs. The thing is, the main source code of StarPU does not have to change when you go to the GPU. That is, the submission of the task is exactly the same. When you move on to GPUs, all you need to do is provide the implementation in the codelet. And that's about it. As long as it has the same computation behavior as the CPU implementation, then there is no reason for any bugs.
Mm-hmm. Thank you. Yeah, that's what I wanted to hear.
That's the idea, that the sequential task flow provides you with a sequential semantic, and you can even debug that sequential semantic. You can ask for just one worker, one CPU worker, so the tasks are just done in any order that respects the dependencies, but without parallelism. And then you can unleash the parallelism to see how well it goes. But as long as you respect the non-global variable principle, there is no reason for any bug. Any other question?
Yes, I have a related question to the allocation of memory. So if my my computational kernels uses several temporal buffers, so when I launch the tasks, I also should provide these temporal buffers, or can be just allocated the task, or the computational kernel can allocate just the memory in there.
As I mentioned in the previous question about this, you can allocate if you want, but it's usually better generally to let StarPU do the allocation, because it will reuse the allocation from one task to the other. For CPU implementations, okay, malloc is really cheap. For GPU allocation, it's quite expensive, so you might want to keep it. For local arrays in CUDA, for instance, you can do your own allocation. That's fine, because that kind of allocation inside CUDA is extremely cheap. That's all the local variables. But for actual buffers in the shared memory, this is expensive. So you'd rather go with Scratch, yes.
Another question that I have is, for these Scratch buffers, do I also have to specify if they are read or the mode? Or?
You just specify Scratch. When you register the data handle, you specify the dimension of the matrix tile, for instance. You don't specify a pointer because it's just temporary. So you specify the size, and when you pass it on to the task, you just specify Scratch. That's all. And the task is allowed to do anything with it. It knows that it has its own buffer, so it can do whatever. It will just find in it the last piece that was left from the previous task. That's basically it.
Okay, another question is, when I usually submit the task, you have a limited number of data handlers that you can send or specify, and usually, I mean, you can modify that when you compile StarPU.
Yeah.
And my question is, why is it by default set like, I don't know, 6 or 8 buffers? What if I want to use more? Is it a penalty in the performance, or?
It's memory penalty, basically. There is no, of course, if you pass 1,000 data, then StarPU will have to compute 1,000 kinds of dependencies, so it will be expensive. But otherwise, if you have twice as much data handles, that will cost twice as much memory for that part of the task. So that's why we set a default to just a few data, because quite often you don't have so many data to pass on. And you can specify it to be more like 16 or whatever the number. If you really have a lot of handles, then instead of doing like this, because maybe you have some tasks which have a lot of data, others which don't, then you can go with the DIN handles array, which allows you to just pass on as many parameters you want. There is no bound on that end. So you can let the default to like 8 data and use DIN handles to pass on how many, as many data you want.
Okay.
Just let me write this DIN handles. And when you are using the task insert helper, you can tell data array. So you pass on an array of data, and that can be any size.
Okay. Okay. Thanks.
Or rather, data array doesn't specify the mode. So, or rather, appear the mode array.
So type handles and.
Okay, if there are no more questions, I'll let you, of course, go on with the hands-on. So, of course, for the people who have already programmed with StarPU and know the basic pieces already, we can discuss more advanced topics. Even if I have slides about more advanced topics that I will show in the second presentation piece. We can discuss about your own source code and your own needs, so that we can get you to the useful features that StarPU can provide.
In the guiding, in the guide, the getting started guide, you mentioned a script called init.sh if we don't have CUDA or OpenCL.
Oh, that's not init, that's simu.sh.
Ah,
That
okay.
was typo. Yeah, I guess I modified it in between.
All right.
This is not up to date.
I see.
Yeah, because in it, the init was not really explicit about simulation or native execution.
Samuel,
Oui.
can you please make me host so I can try to see if I can create a breakout room?
Yeah. It should be now.
Yeah, thank you very much.
So I see on the pad a question about what is the typical use of StarPU in external applications. Is it more StarPU MPI or single node StarPU? We have both. We really have both. For instance, Airbus sells its solver to customers using we StarPU with it to be executed on the desktop of users, basically. So they run on Windows and they just run the application on their own desktop, which is usually a quite strong desktop with like 100 gigabytes of memory and things like this. But they need StarPU because their matrices are like 1 terabyte or 2, and StarPU manages the movement of data between the disk and the main memory. So they are really happy with just one single node because they can run, thanks to the out of core support of StarPU, with just a small amount of memory. But then yes, we have a lot of people using the MPI version to scale. So we have recently had an example at the University of Bordeaux for some metabar coding, and we could achieve some application use case that they wouldn't be able before. So a million matrix side. And that's really thanks to the runtime, the use of a runtime, and the Chameleon software. So just let me put the name Chameleon. It's the dense linear algebra that sits on top of StarPU to provide linear algebra operations already parallelized.
Samuel, I created a breakout room. If people want to have a more private discussion, please let me know who you want to who wants to join the room.
Okay, so if anybody has questions that are more private or maybe not interesting for everybody, you can ask, I guess.
Julien?
Yeah.
I would like to go to a breakout room with Oliver.
Absolutely. So, Carlos with Olivier. Okay.
There is a question that came to my mind. You were speaking about NUMA domains, Samuel, and I was thinking, let's imagine I run on a processor with NUMA domains like EXA2PRO or a recent AMD processor, and I just use one MPI so that all the cores are used for task. I mean for thread task. StarPU is able to optimize the placement of the task, or is aware at least of the NUMA domains, or I should care about it? Samuel? He's in another room.
No, he's not. Samuel, did you hear Mathieu's question?
Yes, but my mic was mute.
Okay.
Okay. Sorry.
So you should not have to care about this kind of thing. So StarPU does have experimental support for NUMA awareness, so that the StarPU would make a copy of the data so you can access them locally, and schedule tasks together on the same NUMA node when they share some data, because then you have affinity and clear affinity through the data.
Okay.
We have not had the opportunity to take the time to really check that it works properly, etc. It does work in terms of semantic. That's not a problem. We test this every day. We're not sure how much it is properly optimized. We haven't really checked, but I mean, if somebody says I need it, it doesn't work properly, then we will have a look, of course.
Okay.
As long as we have an example of misbehavior, we can easily have a look.
I see. Okay. Thank you.
Normally, it should be quite fine, because the heuristics we have in terms of duplicating the data, make the balance between I have to copy the data, which takes time, and but that will allow to have parallelism. This is the same with GPUs. This is the same with loading data from the disk, etc. So it should at least be not too bad. Maybe not as good as what you would obtain by hand, but it should be fine enough. So there is a question, how do we measure the overhead printed by StarPU worker stats? Basically, we subtract the execution time from the actual total time. So I was thinking, yes, here it is. So this is the output that we can typically get. So the total here is really, we look at the clock at the beginning of the execution and at the end of the execution, and this is the total time. So in simulation, it's perfect, of course. On actual CPUs, it could be different depending on the initialization time of each thread started by StarPU. Then the execution time is measured around the calling of the user function. So this is really the time spent in the user function. So actual computation normally. So this is really not StarPU code here in the executing time. Sleeping time is measured as the time between StarPU notices there is no task to do anymore, and it notices there is a task to do again. So it is really a question of lack of parallelism. So here we see that almost all workers are sleeping almost all the time, so except the one that executes a task, which has some execution time and some sleeping time. And the sleeping time here is because we have the time to actually submit a task. And so the overhead here is simply the subtraction between the total time and how much time was spent on actual computation and how much time was lost in lack of parallelism. So basically, this is the rest, that is anything which is data management, task management, and everything. So even in simulation, we have some overhead, which is written here, because we simulate the kind of CUDA overhead, allocation overhead, and all of this. So we see here that, yes, even just executing one task does bring some overhead, mostly due to CUDA for allocating and everything. So the overhead is not measured directly. It's just subtraction from the total, and what we know is useful work, or at least useful or due to the lack of parallelism from the application. So it's not due to StarPU itself. So the StarPU threads are just P threads. So we just call P thread create at the initialization of StarPU once per core, and that's fine. For OpenMP, we have thought, I don't remember if we still have this, we thought about allowing the user to call Pragma OMP parallel so that the application creates the thread and then tells StarPU to use them to execute the task. But at least we have an API, C API, to tell StarPU, don't start threads yourself. I will create the thread and I will call you inside the thread for executing the task on the different CPUs. So we really try to strive for flexibility to accommodate with the different kinds of uses. So that's why a C library, that's why different types of data and everything. So about a C++ interface on top of StarPU, we didn't want to necessarily take the time to do a complete interface in that C++ can use the C API fine. We have a few examples in the source code of StarPU of C++ programs. Of course, you don't have the flexibility for polymorphism and everything like this, but that can be built on top of it with prototyping and everything. About objects, C++ objects that you may want to pass over to stop your tasks, etc. We do have some examples, and we are also building a Python embedding at the moment in the master tree of StarPU. So that would be really objects that are passed between StarPU tasks. So this is possible to use. It's not completely easy, of course, because you have to tell that this is an object, how to pass it on between CPUs and everything. But yes, that's the kind of thing which is possible. So about the question of the timings provided by worker stats, we can see with the mult example, which has several tasks, that since the number of tasks is not exactly a multiple of the number of CPUs, some of the GPUs are executing 2 tasks and others are executing just 1 task. And so we have an imbalance. The execution time of those is indeed of 2 tasks, while the execution time here is just 1 task. And then the sleeping time for those CPUs is indeed significant, like the time of 1 task, simply because they are sleeping while those CPUs are actually executing 2 tasks. And in both cases, the overhead is really small, just the time to execute, to submit on the task. But we see that here, it's really a concern of parallelism and load balancing. So these tasks are quite big. 90 milliseconds is quite long. So you could split it in smaller pieces, and then you would have a smaller amount of imbalance at the end. Okay, so before we go for a break, let's wrap up maybe for the first part of this hands-on session. So I won't go into details of the implementation because that's what basically I had presented with the slides. But let's look at the execution itself. So we have seen here an example of execution with the mult example. So that was here running the mult example, which is a simple matrix multiplication split in some pieces. And since we have several pieces, they can be run in parallel on some CPUs. And as I've said, there is an imbalance between some CPUs because the number is not exactly this, a multiple of the number of CPUs. And here in this example, we don't have any task going to the GPUs because it's a really simple implementation that doesn't have GPU codelets. But if you have a look at gem /sgem, so which is indeed an implementation that has both CPU and GPU implementations. If you look at the StarPU worker stat, then you will notice that in these GPUs and CPUs do get tasks, and so they we have a distributed execution between CPUs and GPUs. And the only thing that was needed for this was indeed to provide the GPU function. So you can look at the implementation itself. So xgem.c, we have the main program which just initializes the matrix and partitions the data. But more importantly here, the source code of the main function is just iterate over x and y and get the pieces of data. So the y piece of A and x piece of B, and then the xy piece of C. So we compute the whole C block in one go, and then we just submit the task and we continue with the rest of the iterations. So this is really just submitting all the tasks, and we don't have to care whether there is a GPU implementation or not. The whole GPU thing is done in the codelet. So here we have the address of the codelet for the computation. So if we look at the definition of the codelet here, so we see this notification of the CPU implementation, but also the CUDA implementation, so a CUBA's call actually. And we have 3 buffers. So this is a gem operation. So we have 2 input data and output data. And we have a performance model. I will discuss this after the break. So the CUBA's implementation here is common. So we get the number of elements and the leading dimension of each tile. So we have the 3 data. So we have to get the information from all 3. And if you look at this GPU implementation, we basically call the CUBA's operation. So we just pass over the where is it? The sub A, so that's the pointer on the matrix A, sub B, the pointer on matrix B, and sub C. And we pass over the leading dimension, so the kernel properly knows that maybe it's a piece of a bigger matrix. And of course, the size and small factors. So that's a trivial gem here in this case. Okay, so that's an example. Of course, you don't need to do this by hand because, as I mentioned, there is Chameleon. Chameleon provides dense linear algebra operations on top of StarPU already. So if your application is basically a Cholesky decomposition, then you can just use Chameleon. You can also use it as an example of how these operations, kublash operations, can be integrated with StarPU. One thing I noted in the tutorial is the kublash init call. So this call is important to make kublash aware of the StarPU streams, so that the operations can indeed avoid any kind of synchronization on the GPUs. So kublash init does whatever is needed for kublash to behave correctly with StarPU. So which scheduler is used by default? So what we did was to use the LWS worker by default, so locality work stealing. We will discuss a bit more in the next session, but basically you can change the scheduler with, for instance, DMDR, DMDS, yeah, let's say DMDR. So the DMDR is a scheduler which knows about the efficiency of the different GPUs. And so here it knows that it can fill the GPUs with a lot of tasks, and then maybe give one task to the CPUs, because even one task will take them a long time to complete. So it doesn't give it much more than this. And then that's fine. So by default, the scheduler is LWS, the locality work stealing. We do not enable smart scheduler like the MDR by default, because this requires performance modeling, which we may not have for all tasks by default. So that's why the user has to say it explicitly. Okay, so let's just have a quick look at the partition vector scale. So task insert filter. So that puts it all together. So the vector scaling example that we've shown, so allocation of the vector, then registration of the vector like we've shown, and then we split the vector in n pieces. So this is the partitioning function, and from then on we don't use the vector handle itself, and instead we go over the n pieces and we insert a task for each piece. So here we get the sub piece of data according to the element I, the piece I of the vector that we are going through thanks to the I loop. So this is trivial parallelism. We just split the vector, but that's how it works basically. Okay, so now I guess we can have a small break. So we had like half an hour. If you have questions, we can of course answer them, but then we meet again at so 11 o'clock for the second part, more advanced part on StarPU, and then more advanced exercises. So that will be for later. We'll come back.
Just a question here.
Yeah, sure.
What I found annoying was that before I wanted to insert the task, I had to create it, and I have just seen this example that creates a task in quite a large loop, so quite many tasks will be created, and I wonder what is your opinion in creating a task just once and submitting it many times? This is possible too, but I did not find that in the examples as a common practice.
So you mean the same time, the same task with the same data that you submit several times?
Yeah, that, of course you change data,
Okay, so you have to change the data. The thing is, let me check. Yes, you can create. So this task in StarPU insert task is just a helper. You can create tasks by hand with StarPU task. It was task, StarPU task creator, and then you can fill the fields, and then you can make a copy. We don't provide a function for this, but you can really do something like StarPU task T2 equal task, and then you can do the task submit of T2 and things like this. So you can copy over the content of a task to another like this, as long as you're not calling like once you have submitted a task, you cannot use it as a template like this. You cannot do something like this, T3 equal T2, because in the meanwhile, StarPU has put some things in T2. But provided that you have not submitted the task yet, you can copy it over if you want. That being said, yes, you still have to fill a whole structure just to provide all the information to StarPU, and that's costly, but there's no real way around this because you have to express it.
Okay, thanks.
Okay. I guess we'll be able to start over.
Yeah, go ahead.
So the second part of the tutorial is about more advanced principles of StarPU. So we won't have hands-on on all of these, but on some of these, the idea is to provide a hint on what is available, even if you don't practice all of them, but at least know that it is there. Then you can go check the documentation, examples, on or ask questions if there are some of the features here that you're interested in, and we can discuss the details. So first, we talked about partitioning, and I said once you have partitioned, you're not allowed to access the whole piece, etc. There is a more recent support, which is asynchronous partitioning, so that the partitioning and unpartitioning is actually submitted inside the task graph. So the idea is that we have two steps. The first is to plan for the partitioning. So it's really very much like we have seen before. We have our vector and we register it, so just like before. And we have a filtering function, just like before, telling the number of pieces that we will split the vector into. But then instead of calling partition, which does the partitioning now, you created an array of handles, and you call partition plan to tell, I want to partition at some point my handle with the filter, and I want the children to be stored in this array. So this is just planning. It's like a FFTW, in which you plan for what you will compute. It's just planning, telling, okay, I have noted that this handle, main handle, may be split into smaller handles at some point, and we will see when that will happen or not. So it's just preparation. And the thing is, from then on, you can access actually both the main handle or the sub handles at will. So a way to see it is here we insert a task on the main handle, so working on the whole handle because it's not partitioned yet. And then you can submit the partitioning of the handle into the pieces. Then you can work on the sub-pieces, so with a for I loop, so work in parallel basically. And then you can submit the unpartitioning of the handle to get back the main handle, and then you can insert a task that works on the main handle. So this is all asynchronous. The data partition call I showed before is synchronous, so it's waiting for all the tasks to complete. Here it's not synchronous, it is asynchronous. So the partition call here terminates immediately, and then you can insert the task. So you're not waiting for the task here to complete. It's just a task graph which says we have one task for the whole data, then we have partitioning, and then work on the subpieces, and then unpartitioning, so a join point of it actually, and then work on the main handle. So this is basically a more complex task graph. And the partition submit and unpartition submit are actually optional. You don't have to call them. StarPU will generate them automatically. So you just insert a task on the whole handle, then on the small handles, and then on the whole handle again. And StarPU will know that there is a dependency between all of these, and partitioning and unpartitioning is needed. So it's all generated automatically. So the cool thing is that then you can just take your handles and submit tasks on them and not have to care about partitioning and partitioning. All of this is automatic. Of course, if you keep submitting a task for the whole data, then for a small part of it, then for the whole data and a small part of it, etc., one after the other, StarPU will have to partition, unpartition, partition, and partition, etc. So it will be expensive in terms of simple overhead, but at least it will work. And then having something which is efficient is just a matter of taking care of course, working on all the pieces before working on the whole piece of data. Okay, so that was an asynchronous partitioning. So we mentioned scratch mode to have a temporary buffer. There's another mode yet, which is reduction mode. So the idea is that when you have several tasks which contribute to a same piece of data, then you can specify this to StarPU. So you have to define a neutral initializer for the contributions and a reduction operator for the reduction. So it is really like the reduction of OpenMP and things like this. You just provide the information how to reduce, so neutral and reduction, and that would work automatically. So how does it work? We have here the neutral initializer. It is just a codelet. Actually, it's a simple codelet that sets the initial value. So here we have a trivial example. So it's just one scalar value. And we say that the neutral value, the neutral operation is to just set it to 0. And then once you have the neutral operation, you can provide the reduction operator. So here again is trivial. We just make the sum of the two contributions and get the result. So it's an accumulation of the contributions here with the plus operation, but that can be anything you want to put in your codelet. And then you tell StarPU that for a given piece of data, so my handle that will accumulate the results, I tell StarPU these are the two operations to reduce the contributions to the data and the initialization. And then when you run the task, when you submit the task, you tell that this is data that you will accumulate into. So typically, when you're doing a dot product of vectors, the eventual result is a single value, but you can compute the dot product in parallel on several CPUs, and each CPU can do its own accumulation of the contributions, and then eventually do reduction of all the contributions. And that's exactly what is happening here. You tell for each block of the vector the operation. So we read two pieces of vector, of two vectors. And then we accumulate the results into what looks like a single data, but actually what StarPU will do behind is allocate a buffer for each CPU so that each CPU can accumulate its own contributions. And it's only at the end, once all the tasks are finished, that StarPU will reduce the values into just one single buffer. Okay, so that was for the reduction. Now we can have some contributions which are not simple maybe to reduce, but which can commute. So for instance, for n-body and structure meshes, when you access in write mode to some data, StarPU will enforce the order of the contributions exactly like the order of the submission. But that can be a poor thing because, for instance, here we are getting contributions at different time during the execution, but because StarPU will respect the ordering, it will have to go through the sequential order that was provided at submission. But maybe if a task terminates earlier, okay, let's take into account the contribution earlier as well. So this is how it looks like. We have a task here which writes to some handle, and then we have two tasks here which also writes to the handle but with a commute flag, which means that StarPU is allowed to start this task or this task first. That is fine. Whichever is available first can start first. So typically that will be decided depending on this other data, whether handle 1 or handle 2 is available first. StarPU will then start the one or the other task first, just in the order of the release of the other dependencies. So this allows for quite a lot of flexibility during the execution. So for contributions like this, it allows the scheduler to make smarter distributions of tasks. And eventually, of course, I have here a task that writes to the data without the commute handle and the commute flag. So this task will wait for both previous tasks to finish because it's not marked as commutable with the others. But all the tasks which have the commute flag can commute with each other. Okay. Now let's talk about performance models for actual optimizations. So the idea is that we want to have estimations of task durations so that we can perform advanced task scheduling, because that actually tells us about the future. What will happen is when this task will finish, when this transfer will be finished and everything. So when the scheduler knows the future, it's much easier to schedule, to have an idea what is best to execute the tasks. And also for performance feedback for the user, for the programmer to have an idea of how well his tasks are going, and the computation kernels, how well they are going. So how do you do this? So you still have your codelet here that has the CPU function, and we have an additional field here, model, that refers to perf model structure here, which basically says, and it tells StarPU, you can use history, you can measure the execution time of tasks and record that in a database, so that later on you can use an average execution time over the previous executions and take that as an estimation of how long it will take. You provide a symbol here just to give the name to the performance model, so that in the tools you have an idea of the names of what performance model is for which kind of task. So in the simplest form, it's really history based, which is indexed by data input size. So when all of your tasks have the same input size, then we will just take the execution time for all of these. If you have different kinds of input sizes, then StarPU will fold the measurements according to the data input size. So that basically StarPU will know for small sizes, input sizes, tasks take that amount of time, and for bigger sizes, it takes that amount of time. For history base, it's really strictly per size, exactly the same size. Then you have regression based and nonlinear regression based, or even multilinear regression based. So you provide the input size in terms of bytes or dimensions of the matrices, and then StarPU can create linear or nonlinear performance models, so regression models, according to what it has seen. So we will see in with examples what it really looks like, what the kind of feedback we get. So let's talk about the feedback. We have two ways of providing the feedback. We have online tools that is during the execution, the application itself can request some statistics we have also a visual debugger that can allow to have some feedback during the execution. But we also have offline tools to look at what happened during an execution and do this offline, so really at rest from a trace file. So we have the performance models I've just discussed, but also trace-based analysis. So let's look at what it looks like. For debugging, we have a tool which is not developed by the University of Bordeaux, but by another team in Spain, I think. So Temanejo, it is a task-based debugger. So it's like GDB debugger, but for tasks. So you have the task graph here, and you can put breakpoints on tasks. So saying, I want to stop the execution when this task starts executing, and then you can inspect the execution of the task. You can go task by task, just like you would go line by line in the debugger and things like this. So it's a really interesting tool to play with. And then we have offline feedback. So first, let's talk about the performance model feedback. So I mentioned history-based, regression-based, and things like this. So we have some command line tools that provide the information on these models. So for instance, the most trivial one is some performance model display, which shows just the raw figures. So here we know that for this amount of input, it took an average this amount of time to perform this computation, and it had some standard deviation, which is much lower than the average, so it's significant. And we made 48 measurements. So yes, we can probably trust the average quite well. The standard deviation is not that big, so we can use this as performance hints, estimations of the completion, the time to complete the task. But we can also draw this. So with different sizes, input sizes, we can draw the time to do the computation according to the size, the input size. So here we have the average execution time on the GPUs. We have two GPUs, one which is blue and which is green. And we see that the two GPUs take the same amount of time for the different sizes. And the CPUs then have a different measured execution time. And we see that for small data sizes, the CPU takes less time because we don't have overhead of CUDA. And for bigger sizes, then it's slower. We don't have the parallelism of CUDA. I mentioned the regression. So this is an example. So we have measured on one CPU, and we have drawn all the measurements, the precise measurements. So each point is one duration of one task. And we can use nonlinear regression. So that's in green. That shows a performance model which is parametric. So it is able to predict the execution time for intermediate sizes or even smaller or bigger sizes thanks to the regression model. So you don't need to make measurements for each and every size that you will use in your application. You just need to make measurement for representative sizes, check the look of the performance model with this command, and then you can say, okay, the performance model is good. I can let StarPU use it to make interpolation of the expected performance of the codelets. There's not only time, there is also the gigaflops. So you can tell StarPU for each task how many flops it achieves, and then StarPU can draw for you the gigaflops and performance. So just dividing the number of flops that you have declared in your task by the amount of time that the task took. And so, for instance, here for the Cholesky decomposition, we see that for small matrix sizes, it's really not efficient, and then it gets more and more efficient for bigger sizes. So we see that, yes, these tile size are probably interesting for the CPU. So this is the kind of feedback that is interesting for the user to have an insight into how performant the implementation is. We also have power. So the measurement of power is not really easy because of the hardware, because hardware is not precise from energy measurement. There is a section in the StarPU manual about this, but once you have measurements for energy, then you can have this kind of figure. So here we have two implementations, two CPU implementations, which have differing compromises between efficiency in terms of energy and efficiency in terms of time. And then just running the two implementations on the hardware and drawing the performance in terms of gigaflops per watt. So that's what StarPU computes automatically when you provide the number of flops, and then it measures the time and the energy. And so it can draw these two curves, which show that one implementation is more efficient for smaller sizes, I mean energy efficient in terms of gigaflops per watt, while the other one is more efficient for bigger sizes. So in the context of the EXA2PRO project, we use this kind of feedback to automatically select which implementation should be used for which intervals of sizes. But otherwise, StarPU can also do this at runtime, just looking at the figures. We also provide this kind of figure, which is the task size according to the data size, but task per task, and type of task per type of task, because people don't necessarily realize how long their tasks take depending on the input size. So this just provides all the measurements in one figure to see that, okay, there is a correlation here apparently for the red tasks, and for the green tasks there is not so much correlation with the task size. So something odd is happening here probably. Okay, now about the trace-based feedback. So you execute your application on a given system, and then you want to have a look at how well it behaved. So we have a tool that collects events during the execution, and then we have a lot of tools to actually look at the result. So what does it look like? First, it looks like this. So this is a Gantt chart. It shows the time in this direction. And here we have the CPUs and a GPU. And it shows in green when the workers are actually executing some tasks. So we have a lot of tasks here. And in red, we have the idle time. So we see that the GPU is finishing the last task while the CPU is idle, which is possibly a good idea for efficiency, because possibly the GPU is much faster than the GPU, or possibly we can notice a load imbalance instead. So thrid is the tool that we use to do this. It allows some zooming, so you can inspect more closely some part of the Gantt chart. You can look at figures, make sure which task this one is, and things like this. So it's really an interactive thing that we use a lot to debug the performance. Another tool is StarVisi. So star virtual visualization, which is basically the same. So we have a Gantt chart here, but with more statistic analysis. So they have separated the idle time from the execution time, so you more easily see the idle time. You also see the number of ready tasks, the number of submitted tasks, the gigaflop rate, the amount of data which is exchanged with GPUs or over the network, and the number of MPI communications which are going on. And here we have also an idea of how the progression within the algorithm is going on. So that's basically our statistics, and you can play with this. You have a default visualization, but then you can tune the visualization to extract the figures you want. It takes some time to get into the R script, but that's really interesting to have a look at more statistics of what is happening. Okay, so that was for the feedback. I wanted to discuss a bit about the distributed submission of tasks with a trivial example. So here we have a very trivial stencil, 1D stencil. So each update here is updating piece I of a big domain, and it reads the previous element and the previous block and the next block, and it updates this block. And it does this a number of times. So for each iteration, it updates the whole domain piece by piece, block by block. And the question is, how do you parallelize this with MPI? So if you go with MPI, pure MPI, what you would do is to say, I will distribute a given number of blocks per MPI rank, and each rank will work between a first block and a last block. And so just looking at the num-blocks per rank, blocks between me times this number and me plus 1 times this number. So each node will work on these blocks between first and last. But before being able to do the update, it has to receive the contribution from the previous block, so from the previous rank, and to receive the contribution from the next block from the next rank. So after receiving the contributions from the previous iteration, it can perform the actual update between first and last. So it does only the blocks it is assigned. And then after doing the update, it can send the results to its neighbors so that the neighbor can receive them at the next iteration, etc. So of course, there's the initialization that is more complex, but let's look at just the main parts for simplicity. So this is what you would do with MPI, pure MPI. When you go with StarPU, it looks really the same. That is, you submit the reception of the contribution from the previous rank for the previous block and from the next rank for the next block. Then you submit the updates, and then you submit the sending of the contributions to the previous rank and next rank. But the difference is that all of this is asynchronous. So this is submitting a task graph which is saying, I will first receive, then I will do the computation, then I will send. And all of this is asynchronous. And that means that anything that can be done early will be done early, as soon as possible. So here, the updates, for instance, don't have to wait. They don't all have to wait for the reception of the contribution from the previous and next node, because some of these can only need to look at the blocks that were computed by the same rank at the previous iteration, which we already have. So it gives some slack in the execution to be able to wait for the other nodes while doing other computations, so that you really overlap the computations with the communications. And so when you wait for all, you're actually waiting for everything, the communications and the tasks. So this is the explicit version. You are telling, I'm receiving, I'm computing, I'm sending to the next one. That's an interesting thing because it's really like MPI, it's scalable over any number of nodes. Each node only does what it has to do. Another version is going implicit. So here we are actually getting back to doing everything, and first, last, I forgot to remove. So first and last should go. You don't have to specify this. So we just back to this version in which we do everything. So we insert a task for all elements of the domain. So it really looks like a sequential version going on just one node. But actually, this can be done by StarPU in a distributed way. All you need to do is to tell StarPU this handle goes on this node. And StarPU will automatically determine that when doing this, if I am responsible for doing this task because I own the node, the data that will be returned to, then I will have to receive maybe the contribution from the node which owns the data handle here and from the other one. And also I will be responsible for sending my results to the other nodes which are doing a task insertion for another task that will actually need my contribution. So you really have just one simple source code which looks sequential, which looks non-distributed, but actually it gets distributed over different nodes. All you have to do is specify the data mapping, telling which handle goes to which MPI rank. Okay, so that was it for the second piece of the talk. So we can discuss if you have questions, of course, before we move on with the second hands-on.
Maybe a small question. So it's very impressive, and I was wondering if you have examples of production runs for production codes that use these advanced features of StarPU and the resulting speedups. Samuel? Yes, me too. I can't hear Samuel. I was wondering if it was only on my side.
Oh, sorry.
Okay.
I missed it.
Yeah,
So we have a lot of examples showing the different features, advanced features of StarPU. And we have examples of production level code. So for instance, Chameleon that will be presented this afternoon. And this is the source code of Chameleon for the Cholesky decomposition. And this is really the distributed version. So we have the for loops that go over the task graph, the whole task graph for Cholesky, and it inserts the task here, but possibly not, just like I've explained. It will actually insert a task only if the data that is manipulated here belongs to the node. And otherwise it will possibly send or receive data. So we have something which looks like sequential source code and can be debugged as it is, but then going to distributed is just enabling the MPI variant of StarPU. And it does provide, like here, a priority on the tasks and things like this. Also here, it provides a hint that after this for loop, the tile AKK will not be used anymore. So that's kind of hint for the runtime to know that, okay, this can be unloaded from the caches and everything. So we have this kind of examples indeed that get the most of StarPU. And for the reduction and commute examples, features, we have the ScaleFMM, so scalable fast multiple method, which does use StarPU. And actually, the commute flag was improved exactly for that application to avoid useless synchronization between tasks. So it goes as much parallel as possible. So we have links on the StarPU websites to different kinds of examples of production level applications. So you can have a look at the source code.
I have another question.
Mm-hmm.
Oh, sorry. Can you mix a normal MPI with StarPU?
Yes, actually, yes. I haven't shown in the slides, but it's basically like I've explained earlier. You can do StarPU data acquire in read-write in write mode, for instance, on the write mode. And once you have, oh, sorry, here it is. So StarPU data acquire in write mode, and then from then on, you can do MPI receive in my buffer, because you have told StarPU that you want to write to the data, to the original buffer that you had allocated and registered, and then you can receive, which will write to the buffer. And once you have received, you can do a StarPU release. So that's one way of doing it. That is, you call MPI yourself. That's not the best way of doing it, because that's synchronous. StarPU data acquire has to wait for all the tasks. So most often we recommend using rather these operations, which do the same, but inserting them into the task graph so they can all happen asynchronously.
Is this your own implementation of MPI, or?
No, it uses MPI, but it synchronizes it with the task execution. So basically what this does is exactly an acquire with a callback that will do the MPI receive. So it's basically what I've shown, but asynchronously.
Okay.
So it's better implemented. But then, for instance, if you have your source code which is already doing some MPI like this, and you don't want to modify this before you want to try StarPU without modifying everything at the same time, you can just here call task insert for the update, and then here do the acquire to wait for the task before doing the send, and similarly for the receive. So that's a way of progressively replacing your code with StarPU calls. And then progressively, once you have modified here the update, you can replace the MPI receive with StarPU MPI receive.
That sounds cool. That's what I actually need for my project. Thanks.
Mm-hmm. And the good thing is, of course, here you have synchronization, you have a barrier here, basically. And once you have gone to the task graph, you don't have the barrier anymore, but at least you have the intermediate step in terms of engineering time.
Mm-hmm. I have another question. It's more related to the first talk. Is what is the difference, for example, to use the buffers in read mode and just to pass these buffers as value, like in cell arcs, for example?
The difference is that you can do this. I mean, if you have some data which is always the same, you can just pass it over here, like this. You can pass over information, whatever information you want to your task. And the bonus is that StarPU will not bring overhead on this, computing dependencies and everything. So if you're only reading the data, then that's fine. You can use global variables. But for execution on GPUs, for instance, that will not work because you have to load the data onto the GPU, and maybe the data is too big for the GPU. So at that point, we'll want to move on with an actual handle.
I'm a little bit confused. You mentioned global data, but before you said you should not use global data.
Well, ideally, you should not use global data. You should pass them over explicitly so that your functions are pure. But basically, when you're passing over a pointer to some existing allocation, you're basically passing a global pointer. That's what I mean. You have some global data that is not managed by StarPU, and you're passing it over on the side without StarPU knowing about it. That's fine, as long as you don't need GPU execution.
Okay, but then what is again, because it was not clear for me, the difference. So passing StarPU value, for example, and StarPU read to the GPU.
Well, in the case of GPUs, passing it with StarPU read will actually make the transfer to the GPU, so the GPU can access to the data. If you pass it with value, then you have to pass a GPU pointer. But then if the task is executed on the CPU, then the GPU pointer is non-valid. So you could pass, you could make your own CPU and GPU copy and then stuff the two pointers in two values. And then depending on the CPU or GPU implementation, you will take the CPU pointer or the GPU pointer. So you can tinker like this. So that's fine. You don't need handles for this kind of case. But if the data that is read is produced by another task, you need a dependency. And then it's way simpler to just to just use a handle, and then StarPU will support the dependency.
Okay.
And also, if the data doesn't fit the GPU, then you will have to load pieces of the data and unload them as required to execute the different tasks. And StarPU can do this for you.
This one's better. Thank you.
I would have yet another question.
Yeah, sure.
So, for example, that you are working on workstation with GPU and many cores and and you are not the only one on the workstation, but you would like to utilize dynamically upon the available CPU cores and GPU resources non-dependent tasks, but you have, for example, million of tasks that actually needs to be done in a parallel, trivially parallel. Is how this detection of the CPU load, GPU load can be handled, or is it possible to dynamically detect the overload or overscrewing by others, for example?
StarPU doesn't implement this yet. We don't look at the state of the system. We assume that we have the machine for ourselves. That being said, it can be made to disable using some cores dynamically, so that you can have like a supervisor that tells StarPU, okay, you can use these cores only, and then later on tell, oh no, don't use that core. You can use that other core instead, or just execute on one core. So I've written in the chat, it is called the knobs. So if you look in the documentation, I don't have slides for this, but in the documentation, you will see the knobs interface, which allows to dynamically specify which workers can be used or not. So we don't implement auto detection. Personally, I find auto detection dangerous, because if you have for instance, 2 StarPUs running at the same time, will they be able to stabilize themselves automatically to using half of the machine? It's not clear. So we think it's better to have some supervision that decides how much is spent on each application, possibly with the help of the user hints saying, for this part, I want to spend half of the machine, for that part, half of the machine, or maybe other figures. And then when one is finished, then the other can dynamically get the CPU cores. Ideally, we will have some stock exchange, I would say, that is the different runtimes that express their need in terms of at the moment I don't have many tasks to do, so other runtimes can use the CPU cores. At some other time I have a lot of tasks to do, so maybe I could use more cores. That's something that was investigated in the InterTwin European project. So Olivier Aumage, who is here, can talk about it. There was some work with the BSc about this.
Yeah. We did a resource manager. So the idea is that we can plug to the BSc dynamic load balancer. It's a kind of a third-party tool that can balance resources between multiple runtime systems, and then this runtime systems can delegate and decide over the course of the execution of the application how many resources are allocated to one runtime system and how many resources are allocated to another runtime system. So this allows to control that. And it can work also between multiple applications. So if you have multiple processes, that can be useful.
Okay, I was wondering if this process management interface of PMI would be somehow of use with this MPI and also for allocating additional.
All the runtime systems that are using this interface have to comply with it. So I don't know if there are any MPI implementation right now that are supporting it, but that can be made probably, yes.
Yeah. So the question was also maybe what if you have, for example, a million independent tasks that takes some time and you would like to submit it, and you could, for example, submit it in a loop and set initial value for it and wait to them to complete. What would be the best approach? Maybe to specify just a smaller portion of tasks so that you do not submit million of tasks at once, but that they will grab a new job dynamically after they finish or somehow like that, but still would overscope the number of tasks with the number of available resources.
So there's one thing you can do actually. I'm pasting in the chat. This environment variable modifies the behavior of task insert. I said that it is non-blocking, so that you can do several of them and they are non-blocking. But actually, when you set StarPU limit max submitted tasks, it will block when there are here 10,000 tasks which were submitted. So you can indeed have your loop which submits millions of tasks, and by just specifying this environment variable, the loop will block automatically when 10,000 tasks have been submitted. And there is this other variable which tells when it should start submitting again. So basically the number of live tasks will be between 9,000 and 10,000 typically. So that's a way of doing it. Of course, you can tune the numbers depending on the number of CPUs and things like this.
Have you ever tried, or another question, it is for, if you, can you prepare, let's say, code that has many codelets types with vector, OpenMP, MPI, GPU codelets, and then actually distribute a binary so that it will dynamically know what it can submit to. So this detection can be this inside the application itself.
Yeah, we don't provide much facility for this because that will really depend on the kind of build tool chain you have. But basically, what you can do is filling the codelet structure dynamically, because here I have specified here I have specified the function pointer statically at compilation time. Let me show here like this. So here it's static, but you can fill these field dynamically in your main function by detecting whether CUDA is available or not, then loading a plugin in your application so that your main application doesn't depend on CUDA being installed, but just some plugin depending on it, and then dynamically fill the structure with the pointers to the functions that are loaded in your plugin. So that's one way of doing it.
The programmer to detect or to configure what architecture or what would it be run on. Of course, there is no facility to detect that inside StarPU.
StarPU will do it. That I mean, provided that all the machines you're running on
if you have a
CUDA.
cluster with just a few GPUs, but you submit everywhere, and then on those GPUs you would like to run those codelets, and this would run faster, but you would also like to utilize other CPU codelets on other nodes.
Yeah.
How this should be done? So this detection needs to be dynamically in some sense.
The thing is, do you have CUDA installed on the machine which don't have a GPU? If you do, then it's fine. You can just distribute the same binary which has CUDA included, and it will run everywhere. And StarPU will just notice whether there is a GPU or not, and then use the implementation or not. But if your nodes, some of your nodes do not have CUDA installed, then you cannot just run your binary as it is. You have to load dynamically a plugin that depends on CUDA. So yeah, that's not something that StarPU itself can solve, because it's your application which is loading some CUDA code or not. But if you can embed just a CUDA library, you can ship the libcuda.so file along your application, and then that will be fine, because it will either find the drivers, the CUDA drivers, or not, and then that will work.
Okay, thank you.
I have another question.
Yeah.
It's about the visualization of the graphs. So, for example, in this thrid, well, I have used it, and all the tasks are always have the same color. And yeah, I was thinking if there is a possibility to specify a color for each task.
Yes, there are several ways of doing it. you have, when you run StarPU FXT tool to generate the trace, you have -C, which will randomly choose a different color for every type of task. So the same type of tasks will have the same color, but the choice of colors is just random. So it is deterministic, at least, depending on the name of the task. So it's always the same, but it's basically random. You can also choose the colors inside the source code of StarPU. You have a color field which you can set in the codelet or even in the task. If you have some tasks which are important and the same task, the same type as other tasks which are less important, you can specify for some tasks a different color. You can also inside Vite choose a different color the way you want. So after the measurement, let me open a different trace. This one will be enough. So in the settings of Vite, you can see the events. No, sorry, the states. So the states here include all the kinds of tasks. So we have the different kinds of states. So when it is sleeping, idle, and everything. Well, my task, that's my task, I think. And so here you can tell I want a different color. So here my example is a bit dumb because I don't have names on tasks, but basically you have the names of the task here and you can change the color. And what you need to do is just to reload the file here with this button, and then it will have changed the color. So red is not a good idea because it's the idle time, of course. But yes, you can specify whichever color you want. And you have seen that you can save this here. You have color sets that you can save to, so make a copy, remove templates. So to quickly reload a set that you have previously chosen. So that the way you prefer, either you can do it after the fact with Vite itself, or you can encode it into your application itself, specifying the colors of the task, and Vite will follow.
Okay. Which option is it to put it in the task? What's the keyword?
I think it's color. Let me check. Color. Yeah. So here it's just a field of the task, and this is RGB value, simply RGB.
RGB. Okay.
And I think there's so there is for the task itself, and possibly for the codelet. So this is the structure task, I think. Yes. And StarPU codelet. I know we didn't as yes, we added it here. So for the codelet is color as well. So again, RGB value.
Okay, thanks.
So for the second part of the hands-on, so that depends, of course, on what you have already done with StarPU, of course. I have put the main things that are important, I believe. Allocation, when you're using GPUs, you should use StarPU malloc because that's the pinned version of the allocation so that the transfers between CPUs and GPUs can proceed asynchronously. If you use just malloc, then it's not pinned, and then it CUDA defaults to a non-efficient version. If you don't want to use malloc and you have your allocation already done, you can pin by hand. So there's a function for this in the StarPU API. So it's memory pin. So you can tell StarPU, this area I have already allocated it, please pin it so that CUDA is efficient. For submission, I mentioned the question of get local stream. One thing you would probably want to do is to avoid synchronizing at the end of your CUDA task. So in our example, some of the examples do some synchronization to wait for the CUDA kernel to be finished before returning from the Kotlin function. But you can remove that call and specify this flag. Maybe let me make it bigger. Async to tell StarPU, I have submitted the work to CUDA. Then you can get back control and notably start data transfers and things like this. And this is the same for OpenCL. Okay, then in the hands-on, we have several examples to show the kind of feedback that we have on the performance. And this is all provided in the simulation mode. So you have the figures already, and you can draw the plots that I've shown in the presentation. Usually you cannot run Ghost View inside your Docker container, but you can copy the file from inside the container to your host so that you can show the image. So this is indeed the performance plot showing the different implementations. And here, this is for the time of one Kotlin, then the gigaflops of the Kotlin, and we see that there is a decrease when the size is more than the cache. So that shows how useful it is to specify the number of flops in the task so that you get this kind of feedback immediately. And then you have energy, so energy measurement, and then combining it with the time and the number of flops to have the efficiency per watt. And then again, of course, when we are out of cache, the efficiency in terms of time is not good. And then in terms of energy efficiency, it's not good either. But then we see that, yes, there's like maximum here. Okay, so we provide simulated results with some measurements that we have made. So you should be getting exactly the same kind of curve, but you can also run it on your own machine. So switching back to the native version, so you have to clean and rebuild everything to run the native execution. But then with calibratical one, you specify that you want to make the measurement, and then you can display the performance. And you can try mult with different tile size to have different measurements here, depending on the tile size, and then get the feedback. What is new is the energy measurement. So it works like the time measurement, except that since it's coarse, what the hardware provides, you can look at the melt bench example, which shows that the idea is you submit a series of tasks of the same time size, and let StarPU take the measurement of this, and then it will take the average along all of these tasks. The thing is, measuring the energy requires administrative access. On some clusters, you will notice that users can access the performance counters for energy. On some others, you wouldn't. So possibly you would have to request root to be able to run the program with measurements. possibly you can ask the administrators of the cluster to enable the energy measurement counters so that you can just run it as a normal user. And notably, Docker doesn't allow reading the performance counter, so you have to really run it outside Docker. So what about the caching of the data in Meltbench? Do you discard the existing cache? No, we don't. That's indeed a question that is the data already in cache or not? That changes, of course, the energy efficiency. We didn't go into that direction yet, but that's the kind of thing we are trying to aim for, cache awareness in the scheduler and in StarPU in general, knowing whether the data is in the cache or not, and then possibly have different performance models depending on whether we know the data is already in the cache or not, because that changes, of course, the performance in terms of time and energy. So for now, we assume the data is in the cache. The thing is, for dense linear algebra, which has driven us a bit in the development of StarPU, quite often the kernels are really cache efficient, and whether the data is already in the cache or not doesn't change that much the execution time. That's not necessarily true, but in what we had seen, it was quite true, so we didn't investigate much more yet. But that's the kind of thing we are looking at. And also we are looking at the simulation of this so that we can experiment with cache-aware schedulers. So I let you play with the hands-on. So depending on what you have already seen, you can go to different sections. And again, we can discuss in private rooms for more specifics. So, but general questions are welcome, I guess. Everybody can benefit from the answers. Yes, external contributions are more than welcome. Of course, that's as usual with free software. We have to discuss because then we have to maintain the contributions. But yes, this is really welcome. So there is a GitLab, and I think we can add external accounts. I don't remember. Natalie, do you know? I don't remember.
Yes, we can add external accounts with persons who don't have an INRIA address. Just send us an email and we can open an account for you.
So that way you can submit merge requests, and then it's easy to discuss over the merge request over the details of the implementations and everything. So in terms of continuous integration coverage, etc., we have nightly tests. So we really monitor this a lot with different, all the test suite of StarPU and different kinds of situations with GPUs, without GPUs, with GPUs only, etc. So some of the results are available publicly, some others are not. I can show you at least this page, for instance. I typed it several times, sorry. I don't know why sometimes Zoom is so slow. Here it is. So this is the performance non-regression curves that tell us whether we have improved or decreased the performance of the schedulers, for instance, and things like this. So it runs every night, and we look at these figures closely. You will notice, for instance, that the task overhead has grown over time between the very first versions of StarPU and nowadays versions, because we have added features and everything. We try to keep it constrained. It's not easy to both have features and a small overhead, but we do track this. And yes, we have benchmarks for Chameleon as well. And so the testing coverage is really good. And that means that when you're contributing, you can run make check to check that you're not breaking everything. And in the merge request management, we do have some pipelines that will try also. And usually what we do is merging, then the nightly checks everything with all kinds of profiles, and we would notice if something breaks and then work together, or otherwise see that it's all green, and then yes, we are really quite confident that it didn't break things. Eventually, possibly if you have a big contribution to make, we can create a branch just for this and then run the nightly tests on this, so that you can work on fixing the issues progressively. And then when it looks all green, we can merge into the master branch. We don't have plans. I mean, we plan to work on StarPU as long as it's interesting and people want it, because it really nourishes our research. It is really a playground for us. So for scheduling, I mean, we could spend our whole career on just StarPU, because there are so many things to do in it. That being said, it may not seem enough for people who want to use it. We are building a consortium between customers, let's say, who want to use StarPU long-term size. And then, yes, the idea would be with the consortium to have some money to make sure that we have engineer time to continue with StarPU, to maintain it over the long run. And then, of course, as long as there are people putting money, then yes, the software can continue existing. But at least for the coming decade, probably we will continue in the research team working on StarPU anyway. Sure, you're welcome, Jose. And see you in maybe next time somewhere. So I wanted to make maybe a small demonstration of the thrid tool, because I know that it's not immediate when you run it the first time. So this is the execution of the Cholesky factorization, and I've just run thrid without doing anything, and we have all these black arrows like this. These are the data transfers. So we have a lot of data transfers between the main memory and the GPUs, because the GPU is not that big, and we have the intermediate results and everything. There's a button here, no arrows, which allows to get rid of them, to only see the tasks, so that you can see what is happening. And what you see is that CPUs here are only doing the blue and yellow tasks, and indeed these are the less efficient tasks on the GPU. So that's why the scheduler noticed that, yes, let's do all the gem tasks on the GPU and none of them on the CPU, because the CPU is much longer. So we have an idea of the Gantt chart. So the CPUs are quite idle quite often, because the CPUs are so much faster. Then there are a lot of things. I won't detail everything, but notably one thing is you can double click on a task that will open a window to tell you about the task. So I have clicked on this task, and it tells me that it is this task. So I called it Chol model 2.1. It's actually a TRSM. It tells me the dates, the duration, and all kinds of information, the number of gigaflop, so the number of operations it took, and things like this. It tells me also things like you can give the coordinates of the matrix tiles, so that you know that this task is working on coordinates x12 and y4. So you have all kinds of information like this by just double clicking on it. You have also figures here. So let's learn something also by clicking on an area like this. So I keep clicking to draw a rectangle. I can zoom to a specific portion of the trace. When I make a right click, I'm getting back to my previous zoom. So I can really zoom with the left click and then zoom back with the right click. So let's zoom on this. So I have my tasks which are bigger, and I see these measurement. These are providing the gigaflops per second measurement. So here, when I double click, it tells me that gigaflops is 18. So this CPU here went at 18 gigaflops during the execution of this task. So it's quite interesting, because it gives you an idea of how efficient it is usually. And notably for GPUs, we see that most often they are at the top gigaflop value when they are doing, let's zoom on here. When it's doing gems, it's really going at maximum 600 gigaflops. But when it's, let's look at maybe this area is interesting. So here we see that with the gem, it's really going at 600 gigaflops. And when going with the TRSM, the blue tasks, it's only going at 138 gigaflops. So it's really not interesting. And when doing these, which are the PO2F, it's only 50 gigaflops. So that way you have a quick grasp of, yes, sometimes it's not that efficient, but most of the time here it is efficient. We also have things like the amount of memory that is used on the GPUs. We have the also the bandwidth being used. So we have all the figures at the same time. When you make a single click, it creates a line with all the figures. So this is small on your screen right now, but you can have it bigger on your when running by yourself. So it can give you quickly the amount of gigaflops without having to open a window and everything. one thing is also when you zoom, you can do a rectangle like this to look at a specific portion, but you can also click in the rule at the top here, which allows to make a zoom, but only on the y-axis, on the x-axis. So to select everything on the y-axis, but select a small portion of time and to zoom and keep all the information. And yeah, this is nested, so you can zoom and zoom again and zoom again several times. And when you right click, it zooms back to the previous level. So you can really focus more and more precisely. And just putting back the arrows, when you zoom, you can really see what is happening, that after the computation of a task here, then the transfer can go to the GPUs, so that then the task there can proceed. In terms of colors, so we have seen red is idle time, so it is lack of parallelism. Purple like this is waiting for data. So this means that maybe the previous task that provides the data has been done, achieved late, and then we are waiting for the data to be able to start the computation. Possibly there is just too many data that we have to transfer over time. And then yes, the bandwidth of the bus is not large enough to be able to overlap completely the transfer with the computation. So when you have small amounts of purple, okay, that's fine. That means that most of the time it's overlapped. But if you tend to see a lot of purple, then it means there's a problem with communication time. Okay, so what is the trace format? It is the page format. I think thrid can open different kinds of formats. I don't remember which ones exactly. But concerning page, I let you just page. There's this. This is the page website, and in the documentation, you have a PDF that tells you the exact syntax. So longpage.pdf is really the exact syntax for the format. Okay, so if there's no more questions, I guess we can finish the session.
Yes. So, thank you very much, Samuel.
Mm-hmm.
It was very interesting. If you have more questions, you can still send us some emails.
Of course, don't hesitate. There is StarPU the mailing list that people can write to get answers. It's better to mail the mailing list, because then any one of Olivier, Nathalie, and I can answer.
Okay, just a small question concerning the web page. Is it something that will be kept?
Yes.
Okay.
Yes, we always keep the previous hands-on web page with the PDF and everything, so people can take the time at home looking at everything. And I believe the Docker image will stay in at least during the duration of the project, so until end of July. So building it will still be possible, and as long as you have made the clone, then you can always run it anyway.
Okay. So thank you again. So we'll close this session soon. I will just stay connected with Julien here in this room. But for the session of this afternoon, then we'll switch to another room.
Okay, thanks for organizing and see you later.
See you and good appetite to everyone.